The goal is to prove this lemma, that witnesses always exist. And recall what that means is that you can find a loop in gamma so that when you take its image under the under this difference of marking maps and you will take the ratios of lengths, then you get exactly the slope of the optimal map. Okay, so and so to set up the proof, we need these definitions. So the first one was the tension graph. So this is simply just the union of edges where the slope is maximal. And then there's this notion of these directions, and then the phi acts as the derivative. So there are these little tangent vectors, and they get sent by the map to tangent vectors in the target. Okay, that's what we have so far. And then so now we can define what a train track structure is, and there's a natural one that comes from this picture. Okay, so the definition is that a train track structure on the graph I don't know, let's just call it delta for now, just any old graph, but we will be interested in the train track structure on the tension graph. Is an equivalence relation on the set of directions T, V, delta at every vertex V in delta. So that's all it is. Train track structure is just an equivalence relation. For every vertex in the graph, you look at all directions that go out of it, and then you impose some equivalence relation on that set. That's what a train track structure is. And in our case, so I want to define a train track structure on the tension graph. Okay, so there's a natural train track structure on the tension graph. Maybe this can go. The tension graph. Let's see this one. Let's do rest a little bit. The tension graph. Delta phi has a natural train track structure. So D is equivalent to D prime. So D and D prime are two of these vectors based at some vertex, like here or maybe here. So they're equivalent if and only if phi star of D is equal to phi star of D prime. If they have the same image. So there's my red pen. So these two are equivalent, right? These the northwest and northeast arrows. They're equivalent to each other. These are equivalent, and these two are also equivalent, but not. So there are two equivalence classes here. So two equivalence classes. The equivalence classes are called gates. Two equivalence classes. The northwest is equivalent to northeast, and southwest is equivalent to southeast. But they're not equivalent to each other, right? And here, nothing is, every vector is equivalent to itself. But other than that, there's nothing. There's no. So these are. So east and west are not equivalent. Okay. Okay, so that's equivalence classes are gates. And then also, when we draw pictures, we draw equivalent directions tangent to each other. Okay, so this is just some kind of a convention. So draw equivalent directions so they are tangent to each other. In other words, we're really supposed to draw this graph like this, right? Two circles that are tangent to each other. Oops, that doesn't look too tangent, but anyway. Okay, that's the way we normally draw these pictures. And we define a path. So an immersed path, or a loop, in delta phi is legal if at every vertex the entering gate is distinct from the exiting gate. In other words, no 180-degree turns, right? In this picture of when things are tangent, you're not allowed to make a 180-degree turn. If you come in through this gate here, you're not allowed to leave through the same gate. You have to go on and well, in this case, you only have two gates, but you can pick either this way or the other way, but you're not allowed to come back. Okay, so this is somehow Thurston's. I mean, it's a variant of Thurston's definition of train tracks. And what you're supposed to imagine is that there are trains running around here, and they're not. A train cannot make a 180-degree turn. It has to go through a gate, one gate in, and a different gate out. On surfaces, there are only two gates normally at every point. But in graphs, you can have more than two gates. So the picture that we sometimes draw is something like a typical picture would be like this. You can have like if there are three gates with two directions in each gate, then the picture would look like this. So here for the definition of legality, you are allowed to make these sharp turns as long as they're not through the same gate. You can come through here and then go this way. That's allowed. That's legal. Okay. So is that clear so far? So now let's, if this is clear, let's make an observation that goes towards proving this lemma. Where are we going? We have to find some loops here, right? We have to find a loop that realizes the distance. So how are we going to find this? So the observation is that any legal loop in the tension graph will work. If you can find a legal loop in the tension graph, then you're done. Okay, so observation. Observe if I don't know, alpha say is a legal loop in delta phi, then the length of alpha in gamma prime is equal to the sigma of f. That's the slope on every edge of the tension graph times the length of alpha in gamma. Right, this is the Lipschitz constant of our function f, or phi. I forget now what the... That's the trouble with taking a break. I don't remember the notation anymore. Phi. So for any curve, you would have this inequality, right? You cannot stretch the length by more than this factor. But if the loop is in the tension graph and is legal, then in fact you get equality here, right? Because all edges in the tension graph get stretched by exactly this number, and being legal means that these gates that you form, the pairs of gates at every vertex are distinct, and that means that the image continues to be immersed. So there is no cancellation when you take the image. Okay, so our only task is somehow to find a legal loop in the tension graph. Okay, so this is maybe the first observation. The second observation is that if every vertex in delta phi has at least 2 gates, then delta phi supports a legal loop. You can have stupid train tracks that don't have any legal loops, right? I could make all directions here equivalent. I can just have one gate. So then there's no way you can go through this vertex because there's only one gate. You cannot go through the vertex in a legal way. There are no legal loops then. But if this doesn't happen, if every vertex has at least 2 gates, then in fact you can find a legal loop. How do you do that? You just keep going, right? You're driving the train, and there's always a way out. And until you, it's a finite graph. Eventually, you'll come back to the same edge with the same orientation, and you'll close up. That's it. Okay, so these observations are somehow very easy. Okay, so the main claim here is that to prove the lemma. Proof of main lemma. We still have to do some work. Okay, it's not the lemma is not completely obvious. So the proof of main lemma. So the claim is that if delta phi has a vertex with only one gate, then phi can be perturbed to an optimal map phi prime from gamma to gamma prime. So it's a different optimal map between the same graphs, such that the tension graph delta phi prime is strictly smaller than the tension graph for phi. Okay? So after perturbing the map, the tension graph decreases. So then, I mean, you keep applying this claim. So if you still have a vertex with one gate, you apply the claim again, and so on. Eventually, you have to get to an optimal map, so whose tension graph doesn't have any vertices with one gate. Now you have to make sure that the tension graph doesn't completely disappear, but that's guaranteed by the fact that this is an optimal map. You cannot do better than this number you have, this sigma phi. That's the optimal map. Okay, so the tension graph cannot completely disappear, and it keeps decreasing. And so the only thing that can possibly happen is that you get to a place where there are no vertices with only one gate. Okay. A priori, the tension graph doesn't have to be even connected. And in fact, it doesn't. I mean, we can make examples where the natural tension graph is not connected. Maybe that's an exercise for you. Okay. Okay, so how do we prove the claim? So proof of claim. So okay, maybe I'll write down what I just said. So claim implies main lemma. So keep approximating phi by optimal maps until no vertex in the tension graph has only one gate. And then use the observations. Then use observations 1 and 2. Okay. You use 2 to find a legal loop, and then you use 1 to say that that loop is the one we want. That's the witness. Okay, so how do you prove the claim? So this is really the main work in this lemma. Right? That's you start with an optimal map, which has a vertex. So here's kind of a picture. Maybe okay, here is a vertex v, and it only has one gate. And maybe there are other things going on. I won't really care about the rest of the graph here. Everything will take place near v. So here I can have other vertices, other edges outside the tension graph. This is all a picture of gamma, and red is the tension graph. Right? There may be edges at v that don't belong to the tension graph. Okay, so what does this look like in the image? So I look at phi, and there is phi of v somewhere, and then there is the image of the red. Now all these red edges go to the same direction, right? That's the assumption here. There's only one gate, so all the red edges at v are going to be mapped in the same direction. So I don't know, they go like this maybe. This is this direction here is this is phi star of d for all of these, well, I don't know. Maybe one of these is d, the other one is d prime in this case, but they all have the same image. Right? That's the assumption about one gate. And these black edges, the ones that are outside the tension graph, they can go anywhere they want. I don't know, they can go in the same direction or a different direction. It doesn't really matter. I'll just for simplicity, I'll draw them in the same way as in the source. So what you're told is that these directions fold, right? In terms of the Stallings, what we were doing in the first day, these two directions are going to fold by phi. Okay, that's the picture. So what do we do now? What's the move? We want to approximate phi by another optimal map so that this picture goes away. This is some other problematic picture here. So what do we do? Any ideas? We are only going to move the image of v, nothing else. Right? I want to, instead of sending v to this point here, I want to send it to some nearby point. Now, in which direction should I do this? The direction of the red, right? That's the preferred direction here. What happens if I do that? If I send it, so I want to pick a point nearby here. This is this point here, and I want to call it phi prime of v. So phi prime is going to be my approximation, and I'm going to take it in the direction of this common, the image direction here. And then I want to extend the map linearly on edges, right? Now, all the other vertices will go to where they went before, and then the map will be extended linearly on edges. So define phi prime of v to be near phi of v in the direction phi star of d for d in t tv of delta phi. Right? So for any d in tv of delta phi, these directions, the image directions, are all the same because it was the same one gate. So just define phi prime of v to be near phi of v in that direction, and also define and phi prime of w is equal to phi of w for all other vertices. All other vertices. And then extend the map linearly on edges. Extend to be linear on edges. Okay. So now, why is that a good map? Why is that a better map? What are the slopes now? If I take one of these red edges, what's the slope on this red edge here of the new map? Well, what's the length of the image of this red edge under phi prime compared to the image under phi? So under phi, it went to some. Let's say this is the image under phi. Now, how does that compare to the new image, which is now, it's from this point to that point? It's shorter, right? So the slope went down. It's no longer this maximal number sigma of phi. It's smaller. On all these red edges, the slope is now strictly smaller than what it was before. So the slope of phi prime on edges of delta phi incident to v is strictly decreases. Right? It's strictly less than what it was before. Okay, well, surely we have to pay the price somewhere. So something must increase. Where does the slope increase? The black lines, but they started out being strictly less. So if my perturbation is small enough, it will still be less than this number sigma of phi. Right? So on other edges incident to v, it might increase. But that doesn't concern us because those edges were outside the tension graph. So the slope might increase on edges of gamma minus delta phi incident to v, but if the perturbation is small enough, the new slope is still less than sigma of phi. Sigma of phi. It stays less than this number. And so that means that the tension graph will lose these edges that were incident to v, and it's not going to gain any new edges. Right? So delta phi prime is strictly less than delta phi. And that's the end of the proof. Okay? Okay, so what's so questions? What's confusing?
I mean, here, if you perturb only a little bit, you still have the V has just only one gate, right? Because the D and D prime are still have the same image under V prime star.
Yes, but the slope will be strictly less. In other words, this is not part of the tension graph anymore.
Oh, I see.
These edges all get removed from the tension graph. The tension graph is only where the slope is maximal, and this is no longer the maximal slope. You can make artificial examples where this kind of thing happens. Let's see. Yeah, I just kind of stretch it out. Yeah, all our examples are on roses, and somehow it's hard to make examples like this on roses. But yeah, I don't know. It's all. It would have to be, the graph would have to be mildly complicated to make an example. But you can kind of imagine that this. You know, you have some big graph where the tension, all tension happens in one part of the graph. Right? So there's some kind of a graph over here where all the tension is, and then the slope is much less on the part of the graph over here. Yeah. But then you take this, say, a vertex like this. And instead of sending, instead of sending it where it wants to go, you start pushing in one direction until, and that's going to increase the slope on all these adjacent edges, until it becomes equal to the maximal slope, and then you'll have a picture like this. So you clearly shouldn't do that, and so this move here of perturbing kind of undoes that. Instead of stretching this edge unnecessarily by this amount, you relax it a little bit by pushing back. That's somehow the idea here. Okay. Okay, now here's a little exercise that I will leave to you. That if you have exercise, suppose delta is a graph with a train track structure with at least 2 gates at every vertex. Then there is a legal loop in delta that looks like one of the following. It could be embedded. So that just means that it's embedded, like this, right? It could be a figure 8, like this. Like for example, if you have a train track structure that has that looks like this, right? There are 2 gates, and the 2 directions within each loop are equivalent. Then you cannot. There is no embedded loop. But there's a figure 8 loop that's legal. And then there's also this kind of a dumbbell picture. For example, if you make a train track that looks kind of like this, then that's the only legal. I mean, you cannot do better than that. So that's it. So those are the 3 possible types. So you can, in every train track with at least 2 gates, you're guaranteed to find a legal loop that looks like this. And this leads to an algorithm to compute distances in outer space without knowing about optimal map, but without first finding the optimal map. Finding the optimal maps might be difficult because it's it relies on Arcella-Ascoli. You have to you take a map and you quickly find out that it's not optimal. But then how do you replace it by an optimal map? But there's an algorithm that doesn't require finding an optimal map. Okay, so what's an algorithm? To compute a distance from gamma to gamma prime without first finding an optimal map. Okay, so you see the algorithm. So you enumerate all loops in gamma that look like one of these 3. And there are finitely many. You can certainly then do this. So we enumerate all loops in gamma that that have one of the three forms over here, right? Either embedded or figure 8 or a dumbbell. Okay. Now for each such loop alpha, compute the ratio. Take length of alpha in gamma prime divided by length of alpha in gamma. I'll do the log of that if you want. And then take the maximal. The maximal of these. Then the maximal value is the distance from gamma to gamma prime. Okay, so this is completely algorithmic, although there's certainly an exponential number. Actually, I don't know. Is it exponential or is it super exponential? The number of such loops. Like how many embedded loops are there in the graph of rank n? I don't know. But certainly for small rank, like rank 3 or something, this is actually feasible. You can do this. Yes.
While you're in the proof of plane, while you're replacing the tension graph is just deleting an edge with only one gate. Then after
only one edge.
After using that procedure, then the new tension graph pi delta pi prime is pi delta pi with one edge removed. That's
not just one, but all edges incident to V. All of these edges, when I move this vertex to the right, all of these edges will actually disappear.
Vertex and edges that contains that vertex leaving out.
Yes, right. All of these. And so, of course, it could be that you have to do this many times because it could be that your tension graph looks kind of like this. There's there's this picture, but then this maybe continues. Maybe there's more of this. Right. So this started out as 2 gates, but once you erase this part here, this becomes 1 gate. So you have to do it again. Yeah. Okay, so this aspect is maybe simpler than the same tachymeter space, if because you can actually compute the distance exactly by some finite process.
Can you give some example of using that algorithm for computing distance?
Sure. Yeah. Computing the distance or computing the distance. Yeah. We can certainly do that. Well, we can go back to our original examples and try to make sure that we that we did everything correctly. I mean, in rank 2, especially if gamma is a rows, then you only have 3 things to check, right? You have to well, no, 4. Like if it's I mean, in this was one of our examples, right? 1/2, 1/2, and these are 1/3. What we have to check is, this loop. We have to check this loop, and then we have to check the loop like this, and then we also have to check a loop like this that goes around. Those 4 loops. You have to you do this process. Wait, so here it's I don't know. For this loop here, it's 1/3 divided by 1/2. No, 2/3 divided by 1/2, right? For this one, it's the same. For this one, it's 2/3 divided by 1, right? And for this one, it's 4/3 divided by 1, right? And so the maximal ones are these 2 and this one. This one is smaller. And you can see that because this one is not legal. Right? The train track structure is like this. So this is the only illegal one in this among these four. So the other three are witnesses. But we didn't have to know, the point is we didn't have to know what the optimal map is in tension graph and train track structure on the tension graph. We didn't have to know this. We just formally compute these lengths and then pick the largest one. Yes?
Maybe in the tension graph, every vertex have one gate.
Can it happen that every vertex is one gate?
Yes.
No. I mean, witnesses will have to be legal loops in the tension graph, no matter what the optimal map is. If you have a witness, it'll have to live in the tension graph of any optimal map, and it'll have to be legal there. So there will always be loops legal loops in the tension graph, no matter what the optimal map is. And so there will have to be gates, vertices with at least two gates. But this kind of a theorem reminds me of, in graph theory there is this famous theorem about the maximal flow, minimal cut. It's the theorem of Menger. Does everybody know this? It's so you have since it's fun, I'll say. So you have let's say you have a graph and you have two vertices in the graph, and you're interested in knowing how many paths that there are from one vertex to the other that don't intersect except at the endpoints. Okay, so this is the number of so maximal flow is the largest number of paths from A to B that are disjoint except for A and B. Okay, so this is called the maximal flow. And the minimal cut, this is the smallest number of points, smallest number of vertices that separate A from B. So if I can find say 3 vertices that separate A from B, then clearly I cannot find 4 disjoint paths, because each path has to go through one of these separating vertices. So it's clear that maximal flow is less than or equal than the minimal cut. Okay, that's obvious. That's kind of like our inequality that the slope, the maximal slope, is the stretch of a curve is less than or equal than the maximal slope. That was an obvious inequality, and then we had to work hard to show that in fact equality holds. And this Menger's theorem is that so Menger's theorem from I don't know when 30s or something is that maximal flow is actually equal to minimal cut. I don't know. I'm not sure what. I mean, I can't really say that this is analogous. But to my mind, this is you have some. You're defining two quantities: one by maximizing something and one by minimizing something, and there's an obvious inequality between them. But then it turns out it's in fact equal. That's exactly the. You have maximum of the ratios, the length in gamma prime of alpha divided by length in gamma of alpha. And that's less than or equal than the minimum of the slopes, sigma of phi, right? This is obvious, but then in fact equality holds, just like in Menger's theorem. Okay. So what are we doing? 20 minutes. How are you doing? Okay, tell me what's confusing. Okay, well, if everything is clear, or maybe nothing is clear, I don't know. We can start with what's going to be the main topic on Monday. I mean, the main thing where this is going is this kind of a classification of automorphisms in terms of some automorphisms are hyperbolic, some are elliptic, some are parabolic, just like in the hyperbolic plane. I don't know if everybody knows about the hyperbolic plane, but that's somehow the model for us. Isometries of a hyperbolic plane can be classified as being elliptic, parabolic, or hyperbolic. So, okay, so maybe this is kind of the last topic. So towards a classification of automorphisms. And for those who know about mapping class group, then this is kind of going to be like the Nielsen-Thurston theory. So in any metric space, so if I have if say phi from x to x is an isometry of a metric space X, then we say that oh, I should, well, okay. The displacement, let's see. How should I say it? Okay, the translation length of phi is, so tau of phi, this is going to be the limit when n goes to infinity of the distance from some x0, say. x0 is a base point. Well, it turns out this doesn't depend on the choice of the base point. To phi to the n of the base point divided by n. Okay, so I start with the base point x0 and I look at the iterates. So phi of x0, there's phi squared of x0, and so on. And these points, I don't know what these points do, but I measure the distance between the original base point and the nth iterate. And this is some number, and maybe naively I expect this to grow linearly. And so that's why I'm dividing by n here, and I'm interested in sort of a speed of going to infinity. And then a little facts from analysis are that this limit always exists. And it is independent of the base point. The fact that it's independent of the base point is not very hard. They just, if you replace x0 by some x1, then these numbers will change by a bounded amount, by maybe twice the distance between x0 and x1. And so by the time you divide by n, this will go away. The fact that the limit always exists, I think this is sometimes called something like a Polya lemma or something like that. It's just a, so this fact, I'm not sure if this is the right name, but anyway. So I think maybe it is. That if you have a sequence of numbers, so a1, a2, these are non-negative numbers, and there's sub-additive. So am plus n is less than or equal than am plus an for every mn. Okay, so our sequence, this sequence here satisfies this by the triangle inequality. Then the limit of an over n exists. Okay. So if you haven't seen this before, you can try to prove it yourself. Okay. So this just follows from the triangle inequality, and the fact that phi is an isometry. Okay. Okay. So then there is a classification. This is just logic, I guess. I mean, so we say that phi is elliptic. Okay, so elliptic if tau of phi is equal to 0 and is realized. So, oh, actually, let's see. I don't think this is what I wanted to do, though. Translation length. Okay, I think I want displacement, though. Sorry about that. I don't really want to take limits here. So I just want to look at the minimal displacement. Okay, so the displacement of phi is the infimum, so d of phi maybe. This is the infimum of the distances between x and phi of x when x is in x. So you want to minimize the distance between a point and its image, and well, you don't know that it's realized, that the infimum is realized, but that's the displacement. I guess this is always greater than or equal than tau of phi. And here I want d, not tau. If d of phi is 0 and is realized. In other words, so this is of course equivalent, i.e. phi fixes a point. Okay, it's elliptic if it fixes a point. Now what else can happen? It can be hyperbolic. It's hyperbolic if d of phi is positive and is realized. And then it's parabolic if it's not realized. If d of phi is not realized. It could be 0 or positive, but it's not realized. Okay? So we want to say something about the automorphisms of free groups as they act on outer space and where they fall in this classification. And the first one we actually already understand. We have a complete characterization of elliptic automorphisms, and you'll tell me why. So the proposition is that phi in out Fn is elliptic in CVN if and only if phi has finite order. Okay, so what's the proof of this? If it's elliptic, right, so what does that mean? By definition, it means that it fixes a point. Well, point stabilizers are finite, so it has to have finite order. What if it has finite order? How do I find a fixed point? Exactly. So that's the Nielsen realization. So this proof is by Nielsen realization. Okay, so the other two are more complicated, and maybe I'll just start with examples of each type. Yes.
When we define a metric in CPN, the metric is not symmetric,
Right.
but we define the what's this? The translation length by the x0.
Yes, x is on the left.
Pi and x0. When we change it to pi and x0 comma x0, then something changes.
If you flip the order, you mean?
Yes.
Yeah. Then that's like computing it for the inverse. Because you right. So the distance. The distance between x and phi of x is the same as the distance between phi inverse of x and x. So it will be like replacing phi by phi inverse. To warn you, there are fun examples of automorphism such that like phi is hyperbolic and phi inverse is parabolic, and stuff like that. So that doesn't happen in mapping class groups, but it does happen for AutoFin. Okay, so what are some examples example? Okay, so I claim that the following, A goes to A, B goes to A, B. I claim this is parabolic. And I claim that the displacement is 0. Okay, so why is that? Well, it cannot be elliptic, right? Because it has infinite order. Right, so infinite order, so hence not elliptic. And so all I have to prove is that the displacement is 0. In other words, I have to find points that move arbitrarily small amount. So if I take, what if I take something like, we saw this picture yesterday, right? It's a sort of a rotation about the missing point at infinity. And so points that move a small amount are going to be points that are close to that point at infinity. So I could take something like, I guess we had this graph on the board today too. This is epsilon, this is 1 minus epsilon. Okay, so A is a very small loop, epsilon. Okay, so how do I find out what the distance is between? So if I call this gamma, what is the distance between gamma and gamma phi? Okay, so what you have to do is look at these standard loops. I mean, I guess we could work out the optimal map and so on, but maybe it's easier just to think about what the critical loops are. So this loop here stays fixed. This A goes to A. So if you have to go through this list of loops, like A, B, and then AB and AB inverse, right? For each of these loops, I have to look at the length in gamma and the length in the image, and then take the ratios. Well, for A, the number is, it's length of A divided by length of A, so it's 1. Because A is fixed, A goes to A, so I just get 1. B goes to AB, so what do I get for B? Well, B goes to AB, so the total length of the image is 1. And then dividing by 1 minus epsilon. Right? The 1 is the length of the image of B, which is AB. And 1 minus epsilon is the length of B, which is 1 minus epsilon. Okay. I don't know. Where does AB go? AB goes to AAB. So AAB, so that means you get 1 plus epsilon divided by 1. And AB inverse, I don't know. Where does that go? AB inverse A or something? AB, so it's A, B inverse, A inverse. And that's, of course, conjugate to B inverse. So this goes to 1 minus epsilon divided by 1. Okay, so the largest one of these is, well, I don't know, it's either this one or this one. Not sure which. Right? This is slightly more than 1. Both of these are slightly more than 1. But as epsilon goes to 0, this converges to 1. And so when you take the log, you go to 0. Right? So this goes to 0 as epsilon goes to 0. So that means that that means that this thing is parabolic. Is that clear? Right, I mean, in the outer space picture, what we're doing is, we have this sort of picture. We're taking a graph gamma that's way out here. This is gamma, right? It's very close to this missing point, and phi of gamma is going to be a point on the next edge, sort of, because this automorphism rotates around all these missing points. And what we're showing is that the distance here goes to 0 as you get closer and closer to the missing vertex. Okay. I guess there is not. Oh, maybe I'll just end with an example. It's not true that all parabolic automorphisms have the displacement equal to 0. There are automorphisms. There are parabolic. It's maybe harder at this point to prove that it's a parabolic, but I'll just say there are parabolic automorphisms with d of phi positive. So it's not just like, in hyperbolic plane there aren't any such. All parabolic isometries have the displacement equal to 0. But both in particular space and in outer space, this is possible. So so this is going to be the main theme on Monday. I'll start by giving examples of hyperbolic automorphisms, and then we'll prove the theorem that says that irreducible automorphisms are hyperbolic. So like the pseudo-Nassau, and the analog of a pseudo-Nassau automorphism is always hyperbolic, and hyperbolic automorphisms come with some kind of a train track structure. So that's what we'll discuss. Okay, enough for today.